So questions 12 through 15 on the review are all about the approximation of a binomial distribution with a normal. So approximate. And to do this, it's helpful to like understand what the binomial distribution is doing. So the binomial distribution is a distribution it's the coin flipping distribution. And by itself, it looks like this. It's a discrete random variable, and it takes outcomes that look sort of like this. So we have a PDF that looks like this, but when there are a lot of flips or these factorials get huge, it becomes it becomes more efficient to approximate this with a normal distribution. So to kind of fit a normal distribution over the top of these. So understanding that this is the binomial distribution we're working with, when we go to do the approximation, in our normal distribution, the probability of some value, so x, the probability of observing x by itself is 0. But we're approximating this binomial distribution, and these things, like these outcomes, are dense because we have a discrete random variable. So what we're going to do is we're going to take our normal distribution and chop it up into these bits. And we're going to chop everything into the parts. And then we're going to say, okay, the probability that I observe this outcome is approximated by the probability of ending up in this region. So we're approximating this binomial with a normal. So normal. Cool. So the way we do this is we use a continuous correction factor. Correction. And basically what we're going to do is for every sort of natural number or every whole number, so for 12, for example, instead of saying the probability of 12, or that x is equal to 12, in our normal distribution is 0, we're going to say the probability that we get 12 is actually the probability that I end up in this range where I subtract 0.5 and add 0.5 from 12. So it's all about sort of finding these chunk points or these break points in this number line and then figuring out what portion of the number line we want. So in this question, we're given a binomial distribution. We are given a binomial distribution where n is 30 and p is 0.4. This means our mean is 12, our variance is 7.2, and our standard deviation is 2.6833. And with this and this, so with a mean and a standard deviation, I can approximate the binomial distribution that's defined by this by using our normal distribution and then a continuous correction factor. So question 12 says, what is the probability that x is equal to, not 12, 10. And what we're going to do is we're going to have our normal distribution with our mean of 12 and our standard deviation equal to this guy. So we're going to use this information and use a normal distribution that sort of has these mean and standard deviation we want. And now we're just going to chop this number line up into this region. So 12 minus 0.5, so 11.5, and 12 plus 0.5. This range in here is the probability that I observe 12 by itself. And we do that for every number. So 10.5, and this is 11, so this is 12. 9.5 for 10. Cool. So for all of these numbers, and we can continue down, and we can go up if we wanted to, but we don't need to for our questions. So what is the probability I observe 10 successes? Is what is the probability we end up in this chunk of the normal distribution? And our endpoints are 9.5 and 10.5. So this is really what is the probability I end up in this range? And we can use our z's to tell us this information. So to copy this over real quick, mu is 12. Our standard deviation is 2.6833. And we want to find the probability that we end up between 10.5 and 9.5. To do this, we need to find the z of 10.5 and the z of 9.5. Looking up the z of 10.5 gives us the probability that we're left of here, and then I want to subtract off the probability I'm left of here to leave me just this chunk. Our z of 10.5 is 10.5 minus the mean of 12 divided by 2.6833. And this is, if I round to the hundredths place, negative 0.56, and a z of, so 9.5 is 9.5 minus 12 over 2.6833. Gives me a z of negative 0.93. So if I look up my z of negative 0.56, I get a probability. So I go to my z table, I find this row, this column. I get a probability of 2.877. And that gives me the probability that I'm left of here, but also includes this extra bit. But I want to cut this probability mass off. So I'm going to subtract off the probability that I see a z of 0.93. So this is, so I go to my z table, I find this is a z of, or this is a probability of 0.1762. So this leaves me with 0.1115. And this is the probability I end up in the chunk that I want to end up in. So the trick with like the binomial approximation of the normal approximation of the binomial distribution is knowing what regions of the normal distribution we're looking for. So question 13 says, what's the probability that x is less than, not equal to, but just less than 11? So if we go back to our normal distribution, and our mean is 12, and here's the area for my 12, and here's the area for my 11 and 10. This threshold is 10.5, and if I want the probability that I'm less than 12, I mean not 12, but 11, it means I want the probability that I get a 10, or a 9, or an 8. So I want all of this space left of 11. So because instead of using like 11 itself, we're going to use the continuous correction factor and say 11 is wide, and 11 actually starts at 10.5. So this is, I want the probability from our normal distribution that we are less than or equal to this. And to do that, I look up the z of 10.5. So this is 10.5 minus 12 over 2.6833. This is again 0.56 and gives me a probability of 0.2877. So that's how we do this. And then the next question says, okay, I want the probability that I'm less than, or what is the probability we observe 11 or fewer, which now means I want to include this, which means this threshold actually starts at and includes 11. So instead of doing the probability that I observe 10.5, I want the probability that I'm less than or equal to 11.5. So I want to start here instead. So the entire trick or like concept with this stuff is knowing how we chop up the number line and being able to identify the specific regions that we're looking for. So for 14 is easy. I look up the z of 11.5 and it gives me some probability. 15 then says, what is the probability I end up between 11 and 8? So now the trick is identifying sort of the thresholds that we want. I want to include 11, 10, 9, and 8. So the lower bound for the range that I want, the upper bound is 11.5. The lower bound is 8 minus 0.5, so 7.5. And I can look up the z's for each of these. So the z of 7.5 is 7.5 minus 12 divided by 2.6833. This gives me a z of negative 1.685. The probability for that is 0.46 or 0.0465. The z of 11.5 is 11.5 minus 12 over 2.6833. That gives me a z of, where is it? Oh no. I think it's 0.19, which implies this probability is 0.42, running out of space. So this minus this gives me this space, and this gives me 0.3787. And this is the answer. And I think the answer key is off at the hundredths place. I think I fat fingered it when I was typing it. But this is how we do these problems. The whole idea is I'm chopping up my number line and finding the region that I want. As soon as you know the ranges that you want, though, it's all back to the normal distribution question. So find the probability that I'm left of some value, subtract the probability that I'm left some other value, and it gives me the range I want. Cool. I hope that helps.